The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Welcome to the second of our SCW series. In this webinar, we will be discussing the details of our solution to this SCW vibration problem, known as the TG Guard. We all recall this picture, and this proves that SCW vibration problem is real and that can be very serious. For those who have not seen it before, this came from a small hydro plant in India owned by the Tata Group. And this means that the generator that it costs so much money for you to procure and then rely on it to make money could be destroyed by this SCW vibration. So in the last webinar, we went through the sequence of this failure mechanism. We explained that there is a vibration which is induced by the structure of the generator, and actually the signal involved in this vibration is precisely 2 times line frequency. And last time I showed you a cartoon to show a pole, rotating rotor, and the 2 poles interact with the stator, giving it 2 times line frequency. We also emphasize that this is electrical in nature, and in fact, if you turn off the current and all of a sudden this signal would disappear. Now, having confirmed that, now we have explained that the vibration is built in. You can't get rid of it. However, you can minimize its effect by keeping things very tight. So if you don't, the loose winding will allow this vibration, and once it gone beyond a certain extent, and it will start to cause rubbing. And rubbing can ablate the insulating mica layer, and partial discharge, you would be able to correlate the increase in vibration amplitude with the incidence of partial discharge activities. Later on, we in a separate webinar will be discussing our new product that will provide partial discharge detection inside the generator. Partial discharge starts is a cyclic process and destroying the balance of the mica, and you will end up in having shorted turns. We frequently hear about that. It is very dangerous. And if you don't have a fire, then your stator will fail anyway. In the last 50 years, everybody is aware of this problem. So during maintenance cycle, I mean major one, they will take out the rotor and start inspecting. Now, there are 2 things you need. One, you need to have experienced technicians, inspectors that are well trained, and they can identify, just like the slide show, this individual, this gentleman, can clearly identify a loose wedge, and then he put an X, and this is a location, identification where they need to re-wedge it and make it very tight. Now, if you think about a large generator, how many of these wedges do you have to inspect? You will be talking about weeks, and during these weeks, unfortunately, the generator won't be running and that means loss of revenue for the power plant. And the second thing about this is the experienced people. I will be going back to this point a little bit later on. They are retiring, and the power plant has been operating for 30, 40 years, and these experienced people are no longer going to be available. So how would you deal with that? Now, a further indication of having a problem of rubbing is this white powder. In a hydrogen-cooled generator, inside the generator, the hydrogen is almost like a storm. It carries these particles, and then it will build up in a place where the flow gets slightly obstructed. Hence, they concentrate in some locations like here. The evidence of the white powder, it shows rubbing has occurred and partial discharge has also happened as well. So by the time you see it, this is already getting to the late stage. And so what we hope to do is introduce you to a concept of much earlier detection, and that is by trending the vibration amplitude. We agree that the vibration is always there. We further agree that looseness enhances its amplitude, which introduces rubbing, and now we will explain to you the details how we solve this problem. To start with, we need a fiber optic sensor called a vibro fiber. And what it is a pair of FBG fiber black grating mirrors sitting side by side, and then they form a cavity. Now, more detail will be given in SEW4, where we will present the whole technology platform. But today, I will just mention it as a reed or diving board. The fiber optic is very fragile, so it is protected by 2 sheets of polyimide. And then this polyimide diving board is formed part of the sensor package. What I've shown you now is the characteristic of this sensor. Now, every mechanical thing, there's always a resonant frequency. But the way we designed this, we can alter the geometry of the diving board and move the resonance any way we like. For example, here we show 700 Hertz as the resonance frequency. Now, since our operating point is around 100 to 120 Hertz, so we are working in this flat region. Okay. Now, in case you are interested in higher frequency signals indicating some other problem, we can move this resonance all the way to 1000, and that is quite easy. Now, if you correlate the sensor linearity, here the experiment involved placing the sensor on a programmable shaker and setting it at 100 Hertz, let's say for instance, then we vary the shaker amplitude, and then correspondingly we measure the sensor output, and you notice that it's extremely linear. By the way, this is not simulated data. This is actual measurement coming from our vibro fiber. Last time we talked about where to install these sensors, and we have a little cross-section of the hydropower generator, but this is now a horizontal view. This also illustrates the problem I have been talking about. Here are the end windings, and you notice they are sticking out from the main body of the stator, and That is the reason why they behave like a mechanical amplifier. If the body vibrates, and the end winding will be vibrating more, maybe 5 to 10 times. Now you also come to understand why the sensor has to be placed here. Because the gap is so small, there is no room for you to place the sensor there. Another thing you want to avoid is to obstruct the hydrogen gas flow, which acts as the main cooling mechanism. So most of the time the cooling gas is fed from the center of the stator structure. They flow outwards. So besides placing vibration/temperature sensor on these end windings, you could also verify if the cooling mechanism is adequate or not by placing some sensor at the lip of the stator. And this is the area where the gas flow will probably have a pressure drop and it will be flowing at the lowest rate, and that becomes the worst case. So just to remind you, we're talking about 6 sensors on each end, so minimum configuration will be 12 sensors. And then if the end winding has a well-defined end cap, then you can capture both tangential and radial direction. Now, today in the reference site that we will show you, unfortunately, the end winding will be cylindrical. So I'm going to explain to you how we tackle the problem. So this slide shows the typical system configuration. Instead of showing all 6 connections, we just, for conceptual reasons, show just 4. Now, by the way, in most generators that are long length, we usually have 2 junction boxes, one on each end. So one end will be the drive end, and another one will be the non-drive end. The junction box collect all the sensor output and then link it to another thing called the composite cable. Okay, by the way, all these sensor cables are purely optical, and they are standard components used in the telecom industry, so it's proven, reliable, and long life. The composite cable has the benefit of keeping the signal in optical form, where it can go for even several kilometers to the control room. And this is why how TG Guard is very different than any competitive product. Competitive product usually have to do the optical to electrical conversion right away on the cover. And the unfortunate thing is that after conversion, the electrical signal will have been conducted by a long cable, electrical cable, acts like an antenna. So they will be, unfortunately, plagued with problems. Sometimes the signal will come with a lot of noise, and if you are not careful, if you don't have access to the time domain original raw data, you might conclude that you have very large RMS vibration peak to peak. It can be fictitious. So it is better to get some time domain signal just to confirm that you are getting the right thing. So now we are ready to talk about the reference site. Okay, we will go through the location of this reference, and also the generator, who makes it, and the size of the generator. And then we'll go through the most difficult part,